So we are on 1B.5 part A, polynomial functions and complex zeros. So I like this unit because I like actually doing computations, and there's computations in this unit. So computations, no, I do not like complications. All right. So basically we understand, hopefully, fingers crossed, how to take a square root, correct? Yeah. And we know the general principle that underneath the square root, you can't have a what? A negative, right? Well, when you have a negative underneath the square root, that's when it turns into what's called a imaginary number. So a complex situation, we start creating some problems for ourselves. So when we have that's going to create an imaginary number. So when I'm taking the square root of -1, it equals what's called I, right? So for example, if you look here and we have the square root of -9, normally we would say no real solution and keep it pushing, right? That's fine, yes, but now we're on our complex solution. So there is a solution. It may not be real, but it exists. So what happens? You're going to separate the negative from the positive. So I'm going to separate and create two separate, whether this is on paper or mentally in your head. If I see the square root of -9 in my mind, I'm going to think square root of 9, square root of -1. Does that make sense? Yes, it's automatically going to be the square root of -1. I'm going to take the square root of the positive, and the square root of 9 is 3. And anytime I have the square root of -1, it equals what? I. So then I end up with 3i. The problem here is that it actually, as we keep going, we're going to end up with plus or minus 3i is going to be our end game. The square root of negative 9 equals plus or minus 3i. Perfect. All right. All right. So do we understand? Are we comfortable with the basic idea of imaginary numbers coming from the square root of a negative? Yes? All right. Let's dive a little deeper. Okay. So complex number. A complex number is a number written in the form of A plus BI. So we're written in the form of A plus BI, where A, 40, 25, where A is the real part of the complex number and BI is the imaginary part of the complex number. No, I just write it so that you can see that it's imaginary. Some people like italicize it and make it cursive and all that pretty, but this is what you're gonna get from me. All right, so we're going to start with the fundamental theorem of algebra. The fundamental theorem of algebra guarantees that any polynomial function x with real number coefficients can be factored completely over the set of complex numbers. So basically, if I have a polynomial function, I can write it in factored form. That is what the fundamental theorem says. So any polynomial function can be written as a multiple of binomials, okay? Where R1, R2, Rn are complex numbers. This means for every complex polynomial function of degree n or greater, n greater than or equal to 1, so n squared, it's square, cubic, quartic, quintic, trying to remember all the names, sectic, hectic. Okay, 6 and 7 have two names. It's either sectic and hectic or septic and heptic. I don't know why. Anyways, octic, nonic, and then goes on from there. But anyways, polynomials, you don't need to know their names. It's not that necessary. But just fun fact, they can be rewritten in this form. And a complex number, so if I have, let's just say, for example, my answer is, our root is 1. Technically, 1 can be written as a complex number. It will be 1 plus 0i. So when it says that they can all be written as complex numbers, that's what it means. Does that make sense? Because technically, this is a complex number. I have a real and imaginary piece. It's just that my imaginary piece would get canceled out. Yes. So this is when it says that they all can be written as complex, this is what it means. Even if it's a real solution, it can still be written as a complex by adding 0i. All right. Okay, let's get to solving. We're going to need to remember the quadratic formula. Who wants to sing with me? Ready? Hit it. What's the quadratic formula? X equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. Hey, okay? Nope. Yep. Might as well accept it. Here we go. Everybody. X equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. Hey, okay? You're going to need to let that be your friend. You got it right. Okay. All right. You're trying not to sing it, but it ends up coming out as a song, Hudson. Yeah, it's cool. So x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. Hey, okay? So in order to use that, though, it has to be in quadratic form, which is why it's called the quadratic formula, okay? So when we look here, we have x cubed minus 6x squared plus 13x. Is that in quadratic form? 4ac. No. I need 100. 25 times 4 is? All right, so we're going to have to factor this first. So that's what it says factor completely. So we're going to factor by using greatest common factor. Does that ring a bell? Yes. What is the GCF between these three terms? X. So I'm going to divide every term by X. When I factor out the GCF of X, I'm left with x squared minus 6x plus 13. Still with me? Now, am I in a quadratic form? Yes. So now can I apply the quadratic formula? Yeah, I can. Your A is always with your x squared. That's your A. Your B is always with your x, and your C is your constant. So A equals 1, B equals -6, and C equals 13. Agreed? And now we just plug everything in where it goes, right? Because that's the beauty of formulas. So someone already did the pattern in the hard work. Our job is now to utilize it. So we get x equals -6 plus or minus the square root of -6 squared minus 4 times 1 times 13 all over 2 times 1. Because I wanted to plug in my b, just as negative b. They were really bored and there was no technology then. It's my theory. They got tired of solving I don't know, something. No, there's a theorem for it. It's a process. That's not part of our class. Oh, I did put it, but I thought I did. Yes, it should be. All right, so now you just got to do the little operations, clean this up a bit. So we're going to get x equals a negative times a negative is a positive. Underneath the square root, we have -6 squared is 36. -4 times 1 is -4. -4 times 13 is what? It's a number. -52. Agree? And 2 times 1 is 2. Is that correct? -4 times 1 is -4. -4 times 13 is -42. So we're going to continue. So now we have 6 plus or minus the square root. What is 36 minus 52? She said 16, guys. She said -16. Yep. I heard you. equals 6 plus or minus. What's the square root of negative 16? Plus or minus what? For what? Say it again. Thank you, Jacob. For I. If I'm taking the square root of a negative, it has to have the I. All over 2.
Oh, yeah.
How did I mess you up? When it's supposed to be at the bottom, I put it at the bottom. Yeah, I'm sorry. All right, so the plus or minus means I have 2 possible solutions to work, correct? So I have 6 plus 4i divided by 2. And I have 6 minus 4i divided by 2. So 6 plus 4i divided by 2. What's 6 divided by 2? What's 6 divided by 2? 4 divided by 2. So this equals 3 plus 2i. That's the imaginary answer. Get it? Yeah, I know. All right, 6 divided by 2 minus 2i. I know y'all are going to complain either way.
So is there no value for square root of -1?
No, it just means that remember, if I have a negative, that means my quadratic never touches the x-axis. So my quadratic is floating in a quadrant. It never is touching. If I have a negative, that means the quadratic isn't going to touch that.
Well, yeah, but why is it not imaginary?
Because there isn't an x, it's not on the x-axis. So the imaginary is letting you know that this is not going to cross the x-axis. All right, so now we have all of our values. So we have 3 plus 2i. We had our GCF, which was our first factor, right? Our GCF was x. That was our first factor, our very first factor. When you are writing a factor for a complex, all you're doing is adding x minus in front of it. Okay, so these are our imaginary zeros, but this is not the factor of it, and it's set to factor completely. Okay, I ran out of room. Do you guys have room on your papers too?
No.
I mean, y'all have space at the bottom. I don't, so I'm just gonna squeeze it in, and then here we go. I'm gonna write it at the top. Is that cool? So in factored form, my first factor is, what is it? My first factor is my GCF that I took out. What was that GCF? X. So this equals x times my imaginary factors, which are minus 3 plus 2i. And my other is x minus 3 minus 2i. And that is it, completely factored.
Wait, why did you put x minus?
For imaginaries, when you're writing the imaginary factor, it's always x minus whatever the complex is. It's always x minus the complex. X minus the complex. Yes.
So the second one, for the factor form, it says negative 3 minus 2.
Yes. On the line, it's this guy right here. 3 minus 2i. I should have put this on its own slide, and I did not. I take the blame for that. All right, so I will write it a little bit bigger, my factored form. So we have, again, the first factor came from our GCF. Are we in agreement? Second factor comes from our complex. Hey, guys, you'll be the first to complain that you didn't understand something. So, yes. The rule for the complex, because when it distributes, it alternates back and forth. So if I was to distribute the negative, it's just going to turn the positive into a negative and turn the negative into a positive. So it just alternates back and forth. That's why it's just always x minus. Because distributing won't change it. Yeah. So we have x minus 3 plus 2i. And then we have x minus 3 minus 2i. And those are going to be, that is it, fully factored. And there's nothing else to do. When it says completely factored, that is it, completely factored. Your GCF is always going to be in front, and then whatever factors you get from the quadratic follow.
This, like, if you look at this, this is what, like, it's ABC, that's what it is.
All right, so next you have number 2, factor completely using complex numbers. So on this one, again, we're going to factor out our GCF. So our GCF here is what? Y. So our GCF that we're factoring out is going to be Y. When I factor out Y, what am I left with? Okay. Now, at this point, could you use quadratic formula? Yes. So you could use quadratic, but there's no point because there's only one term with an X. Okay. When this happens, it's yay, I get to set this equal to 0. I only have one term with X. So instead of using quadratic, I'm going to set the terms equal to 0. And why am I doing that instead of the quadratic formula? It's only one term with a variable. Quadratic has 2 terms with a variable, right? With 2 unlike variables. All right, so now my job is get X by itself. How do I get X by itself? Subtract the 25. She did. We're ignoring her. Equals negative 25. Okay, what's the next step to get X by itself? She just said only divide by 4, in case y'all didn't hear her. Okay, so now X, the variable is by itself. Once the variable is by itself, we're now needing to do what? Square root. When you have a fraction, you're taking the square root of the numerator and the square root of the denominator. It's not just one, it's all. Got it? (11) 1 through 11. So X equals, and again, when we take the square root, it's going to be plus or minus, and what'd you say? 5i over 2. Okay. So those are my X values. So now we're going to write it in factored form. So in factored form, you start with your GCF. What was my GCF? Y.
You would say Y.
Okay. This time, is there a, yes, parenthesis, is there a real piece? Hold on, you're good. I'm gonna ask you and then you keep going. Is there a real part to my imaginary? It's all complex, right? So when you're writing this, I just want y'all to be mindful that this essentially is saying 0 plus or minus 5i over 2. Okay? So when you're writing the factored, is there any point in me writing x minus 0? No. So making sure you just have to write x plus 5i over 2 and x minus 5i over 2. That's because the real piece is a 0. Does that make sense? And there's no point in me writing x minus 0 plus 5i over 2. X minus 0 minus 5i over 2. Does that make sense? Okay, we don't have a real piece here, huh? We don't have a real piece to it, so therefore we don't write that. Okay, how do we feel about factoring with complex numbers? Yes? We did. It's okay. All right, so we're going to move on to the next piece. We're going to talk about multiplicity. So we're going to review multiplicity. If a polynomial function has a factor that is repeated, so when you have a repeated factor, this duplicate roots are labeled as a multiplicity. Multiplicity. It's a really funny movie from the 90s also. Okay, if f has a real 0, c of odd multiplicity, then the graph of f will cross the x-axis at c comma 0, at whatever that value is. So just a regular crossing. It's a c. Yeah, it'll cross at that value. So just like a regular graph, if I had
That's a 0 or C?
c comma 0. So these are just regular crossings, right? They just cross through the graph. Do we see that? Just cross through x-axis. All right, if f has a real 0, c of even multiplicity, then the graph will be tangent. Will be in that stack of unorganized papers. I'll write it down. My life is in shambles. Will be tangent, aka it's going to touch, or I call it kiss the x-axis. I have no clue. Well, maybe you'll remember. So here is it. Kissing the x-axis. Touching, kissing. Do we see that? All right. Oh, I know I left this blank. So odd multiple, huh? So I know why I left this. Do you have an extra blank?
I can put touching kissing outside.
Okay. Well, so cross, we're gonna have to write slash. I call it a drive-by. I can't think of another way of explaining it, but I've always called it a drive-by, and I'm just gonna stick to calling it a drive-by. It will cross or it will drive by. Okay, so the cross is smooth, goes straight through. The drive-by, it's gonna speed up, and then curve its way out. So it's still gonna cross, but it changes the rate of how it crosses. Yes, odd multiplicity. Drive-by. We're gonna see a drive-by in a minute. Okay. We'll see an example of a function drive-by in a minute. Let me clarify. Of a function drive-by. It is what it is. Okay. All right. So you should have this function on your notes, right? We're gonna look at the sketch of it. So notice here we have x plus 2 to the third. X plus 2 to the third means that this is repeated. This is a repeated root, correct? So when we have x plus 2 to the third, it has a odd multiplicity because my exponent is odd. So we have an odd multiplicity. When you have an odd multiplicity greater than 1, this is what happens, the drive-by. It goes, it slows down, then it zooms off. Huh? What'd you say? Yeah. So it goes, slow down, woof, and then goes off. Okay? So hence why in my mind, I've always seen it. Now, this was high school Shauna that called this a drive-by, and grown Shauna still is stuck calling it a drive-by. But it's just an odd multiplicity of 3 or higher. Got it? All right. Of 3 or higher, it's going to create our quote unquote drive-by without the sound effects. Okay, it's crossing, but in a curved way. All right. Now, if we look at x minus 1, so looking at x minus 1, it's squared. So it has what type of multiplicity? It's quadratic, but the word is even multiplicity. Why is it even? Because the power on the factor is even. Okay, and that's when I told you it's going to kiss the line. It goes, and then goes, heck, gross.
So
Functions are crazy.
Odds do drive-bys and evens kiss.
Yep.
As long as they're greater than one, that goes for both.
as long as they're greater than 1. Yep. Well, if it's 1 is odd, so. 1s are boring. They just cross and keep it rolling. A 1 cannot do a drive-by. It just crosses. I didn't say all of that. Did not say all of that. Okay. So when it asks you, where's your multiplicity at? You're going to say it in terms of x. So at x equals -2, it has a multiplicity of 3. Does that make sense? Of 3. At x equals +1, we have a multiplicity of 2.
I mean, always be like, always not even.
Yes. Your power has to be positive. Otherwise, it's not a polynomial. It's a rational. Okay. It's all right. It's okay. Okay. Real words, real terms. This is crossing the x-axis at a change in rate, correct? All right. I'm using the real terms here so we understand. This is tangent to the x-axis. Okay. Crossing the x-axis at a change in rate, tangent to the x-axis. All right. So we know the math vocabulary, but these are friendly ways of remembering what's taking. No, I was not at Waco High when I came up with this. I was at Stony Point High School in 11th grade. So therefore, no. This was just how my 11th grade brain decided to remember this. Okay. So you can use my brain or not, but hopefully it helps. Ignore. All right. Yes. How do we feel about multiplicity?
Great.
Great. All right. The other thing about multiplicity is when you add your multiplicities together, it's going to determine the degree of your polynomial function. Does that make sense? You add your multiplicities together to determine the degree of your polynomial function. There we go. A degree of 5. Why? Because the multiplicity here is. So this is a polynomial of degree. Polynomial.
You saying morning?
No. Of degree 5. Make sense?
So.
All right. So we're going to do a check that you understand all that has taken place. You're going to, at your table, do example number 4. Okay. So example number 4, you're going to look at the graph, identify your roots, and what the multiplicities are. Okay. Don't be confused with a cross and a drive-by. If it's not changing its rate, it is not a drive-by. All right, so first thing first is identifying your zeros, correct? How many zeros do we have? How many? We have 3 zeros. We have a 0 here. We have a 0 here, and we have a 0 here. Agree? Agree. Okay. We all agree at this point. We're going to pretend that we do. So based on our zeros that we have, I should be able to write them in, identify their multiplicity, correct? So my first 0 is at x equals -5, correct? What is the multiplicity there? 1. The multiplicity is 1. It just crosses. It doesn't have any special features. Nope.
Wait, why were the other ones 2?
What do you mean?
Like on the previous example.
Because okay, let me finish this one, then I'll go back to it. So next one's where?
-2.
-2. What's the multiplicity there? 2.
Oh, I understand now.
What is it doing there?
Oh, the biggest time factor, right?
No, had none. It's touching. It is kissing the line. If I'm touching the line, I have an even multiplicity. That's because when I am curving through, when I am crossing but changing rate, that is a multiplicity of 3. That's what happened here. I didn't go straight through. I did not cross. And it's just one, it's just a normal factor, right? That's regular information you already knew. The only new part was the 2 and the 3. You already knew if I just crossed, that's a regular factor. Okay? And then at 2, at x equals 2, it's like 2.1, but we'll just roll with it. There's a multiplicity of 1. Okay? Because I just crossed. I'm not crossing at a changing rate. I'm just crossing, correct? So from here, I can write my factored form or close-up factored form. I know that we have x in factored form. This would be x plus 5 with a multiplicity of 1. Is it necessary to write the 1? No. In factored form, this would be x plus 2 with a 2. In factored form, this would be x minus 2 with a 1 cast with a friendly 1. Would it be necessary to write that? No, but I'm writing so that you can see it.
Try to trick us.
Did not. Okay, so what's the degree?
Degree of 4.
Degree of 4. Why is it a degree of 4? You add up all your multiplicities. 1 plus 2 plus 1 equals 4. Yes. Did it click now? Yes. All right, we're going to try it again. Okay, you're going to try it again. The smallest possible what? This is the smallest possible degree. Yeah, 4 would be the smallest. All right, try it again. Yes, you're trying it again. All right, so it says below is a graph of the polynomial function k of x. Use the graph to create a possible equation for k of x. So the first thing we have to do is identify what our factors are from our zeros, correct? So we have -2, and what is happening at -2? It's touching, right? At -2, it's touching. So it's a multiplicity of 2. Okay. At 3, it's going to be what? 1, because it's crossing. It's a regular old boring factor. Okay. Yes. So that was the part that I need you guys to make sure you're comfortable doing, because this is where we build on from it. It asks us to create a possible equation for k of x, okay? In order to create a possible equation, we have to write it in the form. We're going to write it in the factored form, but we all have to find an a. So step 2 is finding our a value. So the next part is how do we find a? A is telling you whether you are positive or negative, and if you're compressing or stretching. Do y'all remember that value? Okay, we have to find the value of our A. Okay, when we say finding the value of A, that's because this is k of x equals A times our factors, x plus 2 squared times x minus 3. In order to find your A, you're going to use a given point that they provide for you. In this case, anytime you have your y-intercept, that's going to be the value you use. So we're going to use our y-intercept, and our y-intercept at 0, 2. Okay, so it's telling us when x equals 0, y equals 2. So I can plug those in and help me solve for my A. So k of x is going to be 2 equals A. And everywhere there's an x, I'm plugging in 0 because we're using our y-intercept. So we have 0 plus 2 squared times 0 minus 3. do we have the tools and our resources to solve for A now? Yes, we do. So we're going to solve for A. 2 equals A times, what is 0 plus 2? What is 2 squared? 4. What's 0 minus 3? Negative 3. What is 4 times negative 3? A times negative 12. What do I need to do to get A by itself? Divide by negative 12. So we get that our A value equals what? Negative 1/6. Good job. So therefore, this is a symbol that you're going to start seeing a lot more. Then and therefore, that's what this little button means. Then and therefore, because you know mathematicians are lazy, so why not make up a symbol for words we don't want to write? Then and therefore, not what it is. It's then and therefore, k of x equals negative 1/6, and then our factors, x plus 2 squared times x minus 3. And that is our goal, is to be able to find a possible polynomial without a calculator. Impossible. How did it go?
Once or twice.
Yes. Terrible, doable? All right, we're on the last piece. Conjugate root theorem. Okay. Conjugate root theorem. When you hear the word conjugate, you should think of my evil twin. I'm not playing. That's just, okay. It's just the way of thinking about it. It's always its opposite, okay? So for example, if a polynomial with a rational coefficient and an irrational p of x equals 0, so just basically an imaginary, right, conjugate, then if I have a plus the square root of b is a root, then its conjugate, its evil twin, is also. So a minus square root of b is your other one. That's all that it means. If one of my factors is a plus the square root of b, then the other factor has to be a minus the square root of b. Okay, so that's the same for our roots. If I have a plus bi, then I have to have a minus bi, aka my evil twin. Okay. A polynomial function f of odd degree with real coefficient has at least one real zero. So if I am a degree 3, degree 5, degree 7, I can't be all imaginary. Does that make sense? I have to have at least one real, and then the rest could be imaginary. But I have to have at least one point where I cross the x-axis. Okay? All right, so look here. It says we have a polynomial function of degree 5 whose coefficients are real numbers, has the zeros x equals 2, 3i, and 1 plus I. Find the remaining zeros of the function. So we have our real 0, and our real is at x equals 2. Agreed? And then we have 1, 2 complex zeros. And we just said when you have a complex zero, it's going to always have a evil twin, an opposite of it, right? So for this one, I have 3i. So what is its opposite? X has to be what? Negative 3i. That's, and that, no, these are our complex. Okay. So every complex or imaginary pairing has an opposite, and it has to be present. Otherwise, you can't create a root, and I'll model why in a second. All right, so x equals negative 3i. Okay, then where's my other one at? I have 1 plus I, so where's my other imaginary? It has to be at 1 minus I. Okay, this The one doesn't change. Your imaginary is what's changing. Okay. So this is because when you go through the multiplication of your factors, so this would be written as a factor of x minus 3i times x plus 3i, right? When I go through and multiply, what'll happen to my i's? They'll absorb because I squared. Anyone remembers what I squared equals? Not 1. -1. It equals -1. And if I don't have anything to absorb that -1, meant to multiply that I square with, then my function would have i's all in it. So that's why you have to have its opposite so you can have a perfect square factor is what it is. Same thing here. When I would write this in factored form, I would end up with x minus 1 plus I times x minus 1 minus I. And again, when I would FOIL and distribute, my middle terms will combine and my i's will become I squared, and I squared equals what? -1. So the i's will go away. Okay, and we will see that here in a minute. And let's see it all play out. Hopefully, we won't be so mad. All right, so it says find a polynomial function of degree 4 whose coefficients are real numbers and that has the zeros 2, 2, -3 plus I. Assume A equals 1 for the leading coefficient, okay? So we're going to do that first part. We're going to use our zeros. Your zeros come from your factors. Say it with me. My zeros come from my factors, okay? It tells me my A value. What does it say my A value is? 1. So A is 1. Do I need to search for it? Nope. It tells me. So now we're going to write everything in factored form. So we have f of x equals, now I'm going to write 1 for A just so it's there. Is that okay? My first factor comes from my first zero, which is 2. So the factor has to be x minus 2. Agree? My next factor comes from my second factor, my second zero, which is also 2. So it also would be x minus 2. My third factor comes from my third root, which is a complex. It's complex because I have a real plus an imaginary, which makes this a complex number. And it's going to be x minus 3 plus I. And because I have a complex, that means it automatically has a conjugate pair. Okay? Because I have a complex, it automatically has a what? Conjugate pair. And its conjugate pair is going to be x minus -3 minus I. A negative times a negative makes a positive. Yes? Okay? How do we feel about what we just did? Okay? You cannot plug the imaginary piece into the calculator. So you have to do the math to be able to plug it in and create a graph. Okay? So I'm going to have to FOIL, box, whatever method you're comfortable with is going to have to take place here. Okay? So I will review the box method because I assume we all are comfortable with FOIL. Yes. There's an I. There's a plus an I. All right, so I have x minus 3 plus I. I have x. If I knew how to count, I would have 3 boxes. There we go. X plus 3 minus I. And then we're going to multiply. X times x is x squared. X times -3 is -3x. Still with me? X times I is xi. X times +3 is 3x.
Aren't both of them X minus? When you're doing when you factor it or whatever, should it be X minus 3 minus I again, or minus 3?
I had minus a -3. Did I do something wrong?
Oh, wait. Well, why did you change it to plus 3 minus 5? Oh, no, I think
It could be me. We had X minus -3. And then, yeah.
But then wouldn't it be plus on both of them?
Oh, yes. Thank you, Hudson.
Yeah, that's.
Thank you. I told you it could be me. I told you it was me. All right, 3 times 3 is 9. 3 times 3i is 3i. X times negative I is negative xi. Negative I times 3. And negative I times I is I squared is -1. So we get -1 because I squared is, again, I squared equals -1. If you did this right, all of your i's should disappear. Okay? This I cancels out this I. Yes. This I cancels out this I. And all I'm left with is real numbers. So we get f of x equals x minus 2 squared times x squared. Does it have a friend? Does x squared have a friend? Nope, it's by itself. Then we have 3x plus 3x makes 6x. Then we have 9 plus a negative times a negative is a positive. So 9 plus 1, 10. And this is what I can put in the calculator. So now I go to the calculator. So taskbar, calculator. We have x minus 2 squared times x squared plus 6x plus 10. On what? I just wrote down what we wrote on our notes. But I can't zoom on the calculator, that's why. So when I go to graph, Sylvie's thinking, she finally shows me something, but it's not a good view. So notice here how I adjusted my window here to show you what my graph view should be. So how do I change my view on my calculator?
Oh.
Window. We want to go to Windows. So I want to go from -5 to +5. And then I want to go from, on my Y min, I'm just going to go from -10 up to +60. And so that it matches, I'm counting by tens. So now when I hit graph, notice how these are little friends here. Look at them mimicking each other. 10, 20, 30, 40, 50, 60, right? 10, 20, 30, 40, 50, 60. No, look at the graph. What is my X min? How far left do I go? I want to make sure you understand where these numbers came from. Do we see how I adjusted the window? I went to the left. My lowest X is -5. My highest X is +5. It's counting by ones. My lowest Y is -10. My highest Y is 60, and it's counting by tens. Yes? Okay, that's, oh, sorry. That's where those numbers came from. All right. Yes. No, yes, no. Oh, forgot about you. Okay. I didn't mean. Okay. All right, so you're not even getting, stop coughing over here. Okay, so just go. At this point, can you analyze the graph? Yeah. So from looking at this graph, could you tell where there's max or min, where it's increasing or decreasing? What type of concavity it has on a given interval? Yes. Could you tell me if the in behavior, what is it doing as it goes forever to the left? What is it doing as it goes forever to the right? Yes, because that's all the stuff from Unit 1A, right? All those things from Unit 1A is still part of Unit 1B. It's just that we want to make sure that we can get to this point in order to analyze it. Yes? Okay, so when it says identify the characteristics of the function, that's what it's asking. Can you competently identify the characteristics, or do we need to go through finding those things, max, min, x-intercept, intervals of increase, decrease? You think we got it? Okay. The last piece is making sure you can go from factored form to standard polynomial form. Standard polynomial form just means that you have no parentheses and all like terms are combined. Could we do that? What would be the process to go from factored form? You would have to multiple distribution, right? You either can FOIL your way through it or create the box and box your way through it. Does it matter which way you do it? No, it's a personal decision. So making sure we can go. So this again is in factored form. So that's factored. And then we're gonna now go into polynomial standard. Okay. So to get into polynomial standard, we're gonna have to expand. So x minus 2 times x minus 2 times x squared plus 6x plus 10. So expanding this, the first x minus 2 times x minus 2 is going to give me x squared minus 4x plus 4. Huh? You distribute each term to every term. Okay, so if you don't want to do it by multiple distribution, you have the option to use box method. So you have multiple distribution, where I'm now going to take x squared and multiply times x squared, multiply times 6x, multiply times 10. Then I repeat the process. I take negative 4x, multiply it times x squared, multiply it times 6x, multiply it times 10. Yes? And then you repeat the process until every term in the first trinomial has been multiplied by every term in the second trinomial. Okay? How you choose to do it is up to you. If you are a visual learner, I'm just going to use the boxes that are on this table to model it for visual learners. You can always do the box method. So with the box method, you have x squared, negative 4x, and 4. You have x squared, 6x, and 10. And you're filling it in. X squared times x squared is x to the 4th. You add your powers together, right? X squared times negative 4x gives us negative 4x cubed. X squared times 4 gives us 4x squared. X squared times 6x gives us 6x cubed. 6x times negative 4x gives us negative 24x squared. 4 times 6x gives us 24x. 10 times x squared gives us 10x squared. 10 times negative 4 gives us negative 40x. And 10 times 4 gives us 40.
X squared by X squared, X squared by.
Yes, every term in the first trinomial by every term in the second trinomial. Okay? Once, whether you multi-distribute or box method, once you're done, you're going to combine like terms to create your polynomial. So x to the fourth, does it have any friends? Nope. Next, I have my cubes. I have 6 minus 4 cubes. What does that give me? Plus 2x cubed. On my squares, I have 10, negative 24, and 4. What's 10 minus 24? Negative 14 plus 4, negative 10. So minus 10x squared. And then on my x's, I have negative 4, negative 40, and positive 24. Negative 16x. And then my constant is plus 40. And there's my polynomial form. So we had factored and now we have polynomial. How do you feel about either one? Remember, I told you today was going to be heavy on computation, right? I did warn y'all. Starting. It was going to be heavy on computation. It's the first grade for the next 6 weeks. Whatever I wrote on Canvas. Told y'all, once I dump it, I have to make room for other things. All right. Yes, no.